Experiment 47, Microgravity, Microvelocity, and the Speed of Light, Part 1. Okay, I couldn't resist, so I added gravity to this simulation. I wanted to see if the nuclear forces that kept a nucleus grabbing all those protons tightly is really an emergent behavior of charge, gravity, and the unequal diameters of protons and electrons. I had an idea that since a proton could more easily collide with another proton, more easily, say, than an electron could collide with another electron because of its small size, then maybe the nuclear force is the attraction of gravity at this small size that occurs when two protons collide. Now you still have to overcome the electric repulsion force when they're close together, so that's what I wanted to test. I can't just use a formula for gravity versus charge because I think it would be an emergent behavior that occurs with the electron cloud that is orbiting the protons that is also contributing to the effect of holding those protons together. And weird things happen with emergent behavior, as can be seen in my PPS video, so I decided to give it a go. On the way of coding the simulator, I came into some other ideas which I'll describe in this video. I'm still exploring the original idea of the nuclear forces being an emergent behavior of protons, electrons, and their sizes, but that will be in an upcoming video. Stay tuned and subscribe to be notified. Okay, so back to what I discovered along the way. I noticed that if I change the constant of gravity to be very large, the simulation starts to diverge in its behavior. So here I have no gravity. It's just momentum that's bouncing this particle back and forth. But let's add a normal gravitational force of the universe, which I just did, and we will see things start to attract one another very, very slowly. These particles have a mass of 1. They're not quite proton-sized, but this is showing something else that I discovered along the way. Now, if the force of gravity is small enough so that the velocities don't get really big, then the simulation proceeds as normal. But let's turn up gravity and watch what happens when velocity increases. Now, before I do that, I should explain. These two particles happen to be initialized on top of each other, and they're colliding. That's why they're changing colors. In this simulation, a change of color means a bounce has been detected, and I recalculate positions. But since these have initialized on top of each other, they create a bounce which isn't enough to actually get them out of their intersection with each other, and so they're still bouncing back and forth, and in one cycle they bounce toward each other, and the other they try to get away. But this also leads to some interesting behavior. So let's turn up gravity and watch what happens. Okay, so now we see these three guys bouncing. The colors are changing, and they're all getting attracted to each other. Now, these guys, since they're effectively one particle, they're exhibiting some rotational momentum. And I didn't program any torque or any rotational momentum in the simulation, but I'm getting it nonetheless. And that's all just from emergent behavior, which I think is fascinating. But if I turn up gravity too high, what will happen is these other particles will start to intersect each other, and they'll behave like this particle where they can't get apart from each other. And that's where the simulation goes wrong. The velocities get too high, and then the results start to diverge. What I mean by diverge is if you look at the kinetic energy here, it just blows up, and that's because of the simulator's errors. The errors occur when large velocities do not get the time slices to recalculate their positions. So if a particle is moving very fast, it can go in the middle of another particle, or even jump past another particle. The movement is not fine-grained enough to detect a collision when it occurs. Now in the simulation, the way to get more fine-grained calculations is to increase the number of times a particle's position is calculated. Also, I needed to limit the acceleration of a particle so that it can't suddenly accelerate into another particle's boundary. So the constant g in our simulation needs to be small enough that a particle's diameter can't be stepped over when a particle is being accelerated into another particle. Otherwise, a collision would never occur. I started adding realistic versions of g and checks in my code to catch any speeds faster than light. Right off, I found that the double precision used in my code was not enough to keep track of the small differences in position that were near the size of the proton. So I scaled everything up at the expense of being able to simulate a large universe. An interesting note is that the radius of a proton is 8.41 times 10 to the negative 16, whereas the unit of least precision in 64-bit floating point is 1.1 e to the negative 16. So if I wanted to keep this low precision in my calculations, I need to center my simulation around the origin, or else the 52 bits of floating point mantissa would be dedicated to representing a power of 2 times the lowest precision. In other words, adding a proton size to the displacement to any position larger than 2 would result in adding no distance at all. Not good for simulating protons over large distances. I'll have to use 128-bit or even 256-bit floating point in the future. For now, I just scaled my universe's constants to use bigger values, but this will limit the size of my universe. Then I ran into the next big gotcha. In my tests, I allow for protons to get very close to each other. Now, when they're very close, their gravitational attraction goes through the roof, due to this r squared term when r is very low. The resulting velocity from this attraction increases such that their velocity moves the particles way beyond the world's limits. Now I was thinking, how can I limit their speed to avoid this? One way would be to limit how close the protons get to each other. And then I realized our universe already has a mechanism to do this. Charge repulsion. Well, I'm off to implement charge equations next. Stay tuned.